Yo, what's up, guys? We're back with another video. Yes, I may have uploaded just like a few hours ago, but I feel like doing another one because I've been really off schedule and I was just thinking in the shower, just like, I should really like make another video. So this is a little bit more advanced for my Calc 3 people, just in case like, your Calc 2 or whatever, or you want to get like a little bit more advanced. These are some double and triple integral basics. So basically what I'm going to do is just start out with a simple integral. Just start off with integral from 1 to 3 for the bounds, 2x plus 4 dx. All that means is we're just integrating with respect to x. Obviously, you know the drill, x squared plus 4x from 3 to 1. Then you use FTC, x, my fault. 3 squared plus 12 minus 1 plus 4, which is 5. 9 plus 12 is 21, minus 5 is equal to 16. So that's our review, warm up. Now we're going to go into what we call the double integral. And this is where things start getting interesting. There's so many things you could do with a double integral. There's so many more other things you could do with a triple integral. We're going to do this one. 0 to 2, and then 1 to 3. X times y squared, dy dx. I'm going to solve this in two ways if it allows me to. So essentially, we see here that we have two constraints or two variables. Now we have dy and dx. All that means is whichever one is in front, so let's say dx was in front, we would swap it out and integrate with respect to x first. In this case, since this is closest to the variables, which this is like my key, I'm saying this integral is saying that we're going to integrate with respect to y first. Then I'm going to show you a little cool trick if it works out. Essentially, what we're going to do is we're going to keep x constant. However, we're going to integrate with respect to y first. So what we're going to do is I just like to keep everything into one variable for the most part, because you don't want to get too confused. So you just want to integrate with respect to y. So you can do x, y third over 3 from the bounds of 3 to 1. Then from here, you can just plug it in. 3 to the third is 27 over 3. Minus 1 over 3, which is x, 1 over 3. Then you should get 9x minus... Actually, you know what? Not even going to do that. We're just going to do 26 over 3x, because that's what it integrates to. Then from here, you integrate from 0 to 2 because you're not done yet. And this time you integrate with respect to x. So from here, you'll get 26 over 3 times 2x squared all over 2, 0. From here, you just plug things in. You could really divide that by 2. You can make that with 13 over 3. Hopefully, 2 squared, which is 13 times 4. What's 13 times 4? 52. You should get 52 over 3 for this integral. There's this thing, and I'm going to show it later, like in the next integral. It's called Fubini's theorem. Fubini's theorem states, and I don't know what he stated exactly. I don't remember actually. But he stated that we're able to switch out dy and dx, or we're able to switch out the double integral constraints in order to switch the order of integration. He also said that if we have a multiplied integral, I believe, that we're able to separate those, integrate them separately, and then multiply them back together. So our original integral was the bounds of 0 to 2 for x and 1 to 3 for dy. This is what I mean by, let's see if it lets us separate. Instead of doing this whole thing by hand, 0 to 2, 1 to 3, xy squared, dy dx, I believe that what he said was you're able to separate these two and still get the same answer. So look, hear me out. X dx times the integral of 1 to 3 of y squared dy. And from here, you integrate these two separately, so you don't have to keep them as a constant no more. They have their own integral, but you just have to remember to multiply them. From here, we get x squared over 2 from the bounds of 2 to 0. which is just 2 squared 4, 2, which is just 2. Then we can integrate 3 to 1, y squared dy. Keep the 2 on the outside because it's a constant. We can just bring the 2 over 3 out, really. Keep the y over 3 from the bounds of 1 over 3, 3 to 1. Then 2 over 3, 3 squared. 3 cubed is 27 minus 1, which is 26. And we should get the same answer of 52 over 3. So Fubini's theorem states that if we're able to separate these, if they're being multiplied together, then we're able to separate each x and y or whichever other variable you're working with and still get the same answer. He also said that, and this is another example. We're going to do another one with a double integral. So we're going to do this one. The bounds of 0 to 1 and x to 1 of e y squared dy dx. So essentially, let me just redline this. This integral is impossible to solve. I'm not even playing. It's literally impossible. If you want to do it, go ahead, but it's impossible to solve mathematically speaking. Now you might be wondering, why are you asking me this question if it's impossible? If I'm just some sort of dumb college student and you're expecting me to do the impossible, and I'm asking you, yes. However, we have to manipulate the impossible to look possible. When we integrate from y, we're doing it from the bounds of with respect to y. So essentially, when we're saying we're doing it from the bounds of x to 1, this is essentially just saying this is equal to y and this is also equal to y. Same for x. This is equal to x and this is equal to x. So then from here, we can actually draw out the region of where this line is on the Cartesian plane and see where they intersect. So we're able to change the bounds of integration from y to x. We know that y is equal to 1, and we know that x is equal to y. We know that y equals 1 is around here. We also know y equals x, something like this, forming a triangle. Now, since we want to integrate from x to 1, what we have to do is we have to go from left to right. I believe so. Or if you want, you can also do, since you're doing x equals 1, x equals 0, you can just use a triangle and see where you have to go. You know that y goes from 0 to 1. Y is equal to x, then y is equal to 1. So you could really just set these variables up together and say that x is equal to 1. You also know that it starts from 0. So essentially what you could do is you can go here and say that this is y is equal to 0 and y is equal to x. And that way, you're able to integrate with respect to x. So essentially what you could do is, and here's what I mean. Because this is going to be 1 and this is going to be 0. So now you have the new integral of 1 to 0. And then the new integral with respect to x, we're going to do this to x first. From 0 to y. E y squared dx dy. This gives us the ability to just add a constant to ey squared and then integrate such. So essentially right here, we just multiply by y because you just get ey squared. When you add the x here, it just becomes into a y. And now you can integrate from dy. And essentially we turn this whole problem from an impossible function into a function that's able to be solved by integration by parts. So from here, you can start getting your functions ready. Now, since we're doing integration by parts, we already want to change the bounds into u. So we know u of 1 is equal to 1, and then u of 0 is equal to 0. So really nothing changes. Does it really matter? Nah. We know that e to the u is still e to the u when we integrate it. So the bounds are still going to be from 0 to 1. And then from here, we just do the FTC. You know, we just do the bounds of the integral. So it'll be e1 minus 1. And then if you want to simplify that, you could just do e minus 1 over 2. And that'll be your answer. So essentially, Fubini's theorem allows us to change the bounds from x to y or y to x, depending on whatever your situation is, and allows us to integrate easier with a function because we don't want to be integrating e to the y squared. Like that's a big no-no. Don't do that. It takes so much time. Now we're going to be talking about a triple integral. It sounds impossible, yes, but at the same time, it's really, really not. Here's what I mean. Let's say we had the triple integral of 0 to 1, 0 to 2, and 0 to 3. For x, y, z, now we're adding the z coordinate for dz, dy, and dx. You might be wondering to yourself how you might integrate this. All you have to do really is just, such as a double integral, just go in respect to z, then y, then x, depending on which one's closest to the variables. And that's really it. It's just longer. It's just tedious. People look at these and get scared. However, it's not that scary. It's okay. I promise y'all it's okay. So what I like to do is I just like to take these integrals with respect to each one at a time. Yes, it looks wrong and it probably is wrong and I probably got marked some points, but this is just a way for me to keep track of where everything is. So since we're integrating to respect to z first, what we can do is we can just keep x, y as a constant and then divide that over 2, make z squared, then go from the bounds of 3 to 0, and we just get x, y, 9 over 2. 9xy over 2. And we can do the same thing for this. Just add the integral from 0 to 2 for dy, and you get 9 over 4xy squared from 2 to 0, which is equal to 9 over 4x, 2 squared is 4. Boom, so you just get 9x. We'll put it over here. And then the final bound is from 0 to 1 for dx. From here, it's a simple integration, 9 over 2x squared from 1 to 0. And you get 9 over 2 as your answer. So essentially, this is just, I think, a simple box integral, I believe. It's just showing you how triple integrals work. They're not that different from one. You just integrate, integrate, integrate again. It may get more difficult, but this is just a basic video. Now we're going to go into an integral that has variables. It sounds scary. It's not. I promise you it's not. So we're going to do the integral of 0 to 2, 0 to x, and then 0 to y, of 2 dz, dy, and dx. Essentially, we're doing the same thing that we did in Fubini's. We're just going to use the variables as bounds themselves. From there, we're going to integrate with respect to each variable, and we should be good from there. So essentially, we have the integral of 0 to y of 2 dz, which is just equal to 2z from the bounds of y 0. So we just get 2y. Then we can integrate again from 0 to x of dy, and you would just get y squared of x over 0, x to 0. Then you get x squared. And then you do the same thing all over again from 0 to 2 for dx, and you get x to the third over 3 from 2 to 0. And your final answer for this big integral is just 8/3. These are just some of the basic integrals that you might see in Calc 3. Obviously nothing related to a test. However, this is just a basic video to get you introduced into integrals if you are interested though. If you're in Calc 1, Calc 2. They're not that scary. Oh, that's my other video. They're not that scary though. You shouldn't worry about them at all. They're just big symbols for things that are kind of meaningless. I want to get a job, but this has been the basics of double and triple integrals. Just integrate all over them. Fubini's theorem, if you cannot integrate it, find another way. That's the method. Always do it. Thank you for watching though. This has been the basics of double and triple integrals. Hopefully y'all took at least a small part out of it. Thank you for watching, and goodbye.